So today, what we're going to be talking about is defects in crystals. I sometimes like to call the tiniest engineering tool. But before we talk too much about that, I want to tell you a little bit about myself. A little bit about me is I'm from Bainbridge Island. So it's a small town just outside of Seattle. And I have, a love of games. So I really love to play board games. It's one of the fun things that I do for most of my weekends. I have 2 pet tortoises, and I've loved turtles and tortoises for my whole life. So it's a very defining characteristic of me. And I've always been curious. Even when I was a very young girl, I really loved exploring the world, picking things up, seeing just kind of what there is out there, and what can I touch and interact and feel. As a student, I started at a very small grade school. So my grade school was actually kindergarten all the way through 8th grade. And it was a really, really fun place. It was on a little farm, and I actually got a lot of chances to go outside and kind of continue exploring in the way that I really loved for the natural world. For high school, I went to an all-girls high school in Seattle. So I actually got to take a boat every day to school. So it was a little bit of a long trek, but it was really, really meaningful to me because I loved my education there. I really got introduced into science and engineering, and I got to do labs, and I was like, this is for me. I like this a lot. So when I went to college, I ended up going to MIT, which is a technical institute on the East Coast, and I studied material science. And this is really where my passion for science and engineering took off, and this was really what took hold of me in my excitement. So material science is really one of the ways I define myself as a scientist and an engineer, and it's a lot of what I'm going to talk about today. So after I graduated from MIT, where I ended up is here at Caltech, and I'm a PhD student in material science. So that means that I'm studying things about materials and how do we really understand what's going on with those materials on a really, really tiny length scale. So before I talk a little bit more about my work, I also want to kind of go back to the fact that really I'm an adventurous explorer. I love going out and traveling to places, going on road trips, skiing. I really like exploring just everything around me. And that translates not just to all these adventures outside, but also to me in the lab. So as a material scientist, I think one of my favorite things is that I get to connect the physical world with kind of this scientific world of how do we understand something, what's going on with those atoms, and how does that connect to what I'm physically feeling or interacting or designing for the world. So I think Marie Curie said it best. There's nothing more wonderful than being a scientist. Nowhere I would rather be than in my lab, staining up my clothes, getting paid to play. So I want you to start thinking a little bit like a material scientist and think about 5 different materials around you. So I picked 5 from just my desk, and here I have a paper, some ceramic figurines, a bronze beaver, magnets, and an abalone shell. Now we're going to think about how do we characterize those materials. So as a material scientist, we think a lot about how do we characterize materials, how do we think about materials. So let's characterize these 5 materials. First, I'm going to do optical, which is how do they look? Are they not shiny, or are they shiny? We've kind of divided them into 2 categories. We've got paper and ceramics on one side, the shell, bronze, beaver, and magnets on the other. But what if I chose a different category, like where they come from? We could do organic, so from plants and animals, or something inorganic, let's say extracted from the ground. So now we've got a different mixing of materials. I'll show you a 3rd example, which is mechanics. So that's what happens when you push or pull or break something. Maybe it tears, maybe it shatters, maybe it bends. And we see we have an even different mixing of materials in their categories. So why is this? Why are they in different categories? And this is really the core of the question of material science. So what we do is we look at what is the structure of material, how was it processed, what are its properties, and we try to understand what's going on, why it's that way, and then we use that why and that how to engineer new different materials that can do things like take us to space or make really, really tiny electronics. So now I'm going to get a little bit into the meat of the talk, which is what are defects in crystals. So in order to do that, I got to define a couple things. So what is a crystal? A crystal we might think about as, some salts or some pretty gems or other stuff like that. But another way we can think about it is on the atomic scale. So on the atomic scale, we see that what we have is this ordering of atoms. So they have this really regular periodic ordering, meaning that you can kind of copy and paste them throughout a whole bunch of space, and you see the same repeating pattern over and over and over again. So a crystal is a material with a repeating atomic level pattern. One of the fun things about crystals is, like people, it's the defects that make them interesting. And this is where my real love in materials comes to place, which is in defects. So what are defects? Defects is a change in the repeating pattern of the crystal. So if we take our little box here, which is a perfect crystal, they're all nice and ordered. What happens if we have a missing atom? Okay, that's a defect. What about some extra atoms? We could even have kind of a weird mix like this one. Not really sure if it's missing an atom or if there's an extra atom in there. But we could have a different atom instead of the one we were expecting, or we could just have a different pattern altogether that's showing up. These are all different kinds of defects. So next, I have a challenge for you. I'm going to have you find some defects. So in this image, there's a bunch of different defects hidden, and I'm going to give you a little bit of time to figure out how many you can spot. Here are all the defects. So these are the defects. Hopefully you found a couple of them. And now I'm going to explain what we do with these defects as an engineer in material science. So I'm going to focus on this one right here. It's called a substitutional defect. And it's a little extra defect that's stuck in between those atoms in our crystal lattice. And specifically, I'm going to talk about steel. So you might have heard of steel before. It's a very, very common material in building things in a lot of large kind of structures, and it's very, very prevalent. Steel is essentially iron with some carbon wedged in there. So when we think about iron, we've got a structure that looks like this. So those round spheres are atoms, and they're all nicely packed in there. But if you notice, there's not really a lot of room for that iron to sit in between those atoms. But if we heat it up, what we can do is we can change the structure. So now there's space for those carbon atoms, and we inject a lot of energy into the system. So just like, when you've got some extra energy and it's way easier to move around, maybe you're kind of scurrying all over the place, it's way easier for these atoms to move around, to find spots, and to wedge themselves in when there's extra heat or energy in the system. Now, the problem with this is that we're kind of stuck at a high temperature system. This isn't very good if I want to have a building that's, at our normal kind of temperatures that we operate at. So what we do is we got to cool it down really quickly. And when we cool it down really quickly, we don't give those carbon atoms a chance to move out of their places. They can't wiggle into a new place. They are stuck in those little extra spaces between the atoms. And now, as you've moved it back to that structure, you've locked the system. That system really has a hard time moving because you've wedged in those extra atoms. It's not easy for the atoms to move past each other because the carbon is stuck in there. And this is what we call high-strength steel. So this is how we're able to increase the properties of steel. We're able to make them stronger and better for a lot of applications by really wedging in that extra carbon atom. So that's one way in which we use defects to engineer a material. But there's a lot of different ways in which you can design and control material properties using defects. So I have a couple of different fields up here, from sensors and electronics to energy, structural materials, and photonics. And all of these use defects. For sensors and energy, it's a lot of these vacancies, so missing atoms, or these single point of atoms that are maybe stuck in the lattice or stuck in those extra spaces. For electronics and photonics, which is the study of how electrons or electricity interacts with materials, photonics is light in materials, we see kind of similarly, there's a slightly different set, but there's a lot of different of these defects that we use to build these structures. For structural materials, we also use these precipitates, so that's a whole bunch of a different kind of atoms kind of stuck in there as their own little group. But altogether, all of these fields and many more fields use defects to design and push the properties of materials. So how do we study defects? This is what I really do in my work, and actually that big picture there is of one of the microscopes I use. So it's a super powerful microscope that actually lets me get atomic level resolution of my things. So I can just see it. What exists? What am I looking at? The other thing I can do is I can do experimental testing. So what do we do when we control it? How does it break in this particular way? Why is it doing this when I apply this kind of force or this kind of stimulus? Some other tools that we have to understand defects are called simulations. So simulations is using a computer to start tracking those atoms and understanding kind of what are they doing. On the atoms length scale, what's going on? What are they doing? And lastly, we have theory. So theory is really kind of what is that physics problem? What is that problem on pen and paper that I can solve that lets me predict what's going to happen next? So here I have a really fun video. I'm just going to watch it to start. And what we have here is a video of dislocations in action. So this is a kind of defect. It's that kind of defect. And those dark black lines are the defects themselves. And these are generated by pulling the material kind of in that long direction. And as we pull that material, these defects are created and generated, and they're actually what gives us the material-specific properties. So these defects are what allow a metal to be bent when a ceramic would just crack and break. So here we're watching them move, and as we understand the ways in which we move, we can start to say, all right, if it moves this way and we get a lot of ductility, we get a lot of motion and bending, then as we engineer and let it do that more and more and more, we can increase the ductile properties, or maybe we can tweak it in a different way to create a metal in the way we want for a particular application. The other thing that we see here is that it forms these structures within the material. So play it once more. And you can see those structures that are forming as those long lines bend and twist. And so we can use some of our knowledge of, what's going on kind of with that atomic level, and use those structures to then build up those properties and engineer the material. We can also do these teeny tiny tests. So right here we see that there's some grips. So those are the machine itself, and it's pulling up this little sample. So the sample is 1/100th the width of a hair. That's really, really small. And one of the other fun things about this is that this tool is actually used in my research. So this is one of the machines that I work with. And this video actually lets us see, okay, mechanically, we're going to measure out something. We're going to measure the forces associated with pulling on this material, and we get to watch and see what happens. So generally for this material, if I pull on it, it should just break. It should just shatter and break. Let's see what happens here. All right, so instead of breaking, now we're starting to stretch it. And it finally broke, but it took a while for it to break. And that's something that we can start to go, that's unusual. Why is that happening? And we can start getting back to what is it that's allowing us to see these sorts of properties. For simulations, they're really pretty, they're super colorful, and they really give us that atomic level insight. So they tell us what's going on with the atoms that let us have these properties. And for theory, this is oftentimes kind of worked out on pen and paper. So if you see in the upper left, there's a schematic showing, this is the way the light should bend based on what we know from our physics and our math problems. Below it, you see actually the experiment that shows, yep, that's pretty much how it turned out. You can also see in the right-hand side are my notes. So those are actually problems that I was working through, trying to solve how would something kind of come together, how would it work, how would it turn out, to really understand what's going on with these materials. So theory allows us to predict how defects will behave and how they impact material properties. So what's awesome about material science and engineering? What I find is really awesome is that it's a way to connect atomic level structure to macroscopic properties. So what are the atoms doing, and what does that mean for the things that I'm actually touching and I'm actually pushing on, for the buildings that I make and the devices that I design? Plus, you get to tell atoms what to do, and that in and of itself is pretty cool. So that's why I like material science and engineering, and hopefully I've inspired you to think the world a little bit more in terms of materials and a little bit more excitement for all of the things that you can touch. If you are interested in some more resources, I recommend some of these books, podcasts, and talks as fun ways of learning both about some nanoscience as well as materials and the way in which materials impact us in our world. Thank you so much for listening, and I hope you have a great rest of your science journeys.
Thank you for attending today's Science Journey presentation. Here at Caltech, we thank Mitch Aiken and Kitty Cahalan of the Center for Teaching, Learning, and Outreach, as well as Mary Herrera and Kara Steeman from the Office of Public Programming, and the teams from Academic Media Technologies and Event Productions. And special thanks to Robin Javier and Brian Brophy. Additionally, we thank the Caltech Employees Federal Credit Union, the Friends of Beckman Auditorium, and our many sponsors who make these programs possible. We look forward to you joining us again for future science lectures and performing arts events. Learn more by visiting events.caltech.edu.